In this video, we're going to talk about structural robustness and attack tolerance. So what is robustness? In a network or graph theoretic sense, it's the ability of the network to withstand perturbations, or shall we say attacks, or a change in the structure without losing its defining properties. So for example, if we say a graph is connected, then how many vertices would you have to remove before the graph is no longer connected? So let's look at this star graph. Notice that this star graph, in the sense of connectivity, is not robust because we could remove the central vertex and the graph is no longer connected. So just one vertex will change that property. Also notice that the star graph, we call it the star graph for obvious reasons. It looks like a star, but it is also a bipartite. In fact, a complete bipartite graph. If we notice that all of the vertices on the periphery are not connected, they can all be in the same partite set. And so if there are m vertices in the periphery, this is a K1M. But the single vertex in the one partite set then will, if removed, will disconnect the graph. There's a whole collection of work done in graph theory on what is the graph theory analog to robustness. And in graph theory, it's typically called critical graphs. So the star graph is a critical graph with respect to connectivity because the change of a single vertex will change its connectivity measure. Now, in network science, it's important to discuss the different kinds of attacks. Is the attack random, or is it an intentional attack? Why would that matter? Well, let's just go back to the star graph again. If the attack is intentional, then we would assume that the attacker will take out the central vertex because that's a point of where it's vulnerable. However, if the attack is random and we have a large number of vertices on the periphery, there's no reason to assume that a random attack would attack the central vertex. So whether an attack is random or intentional is important to us in the design or the study of the network's robustness. In the random graph, what's interesting there is it doesn't matter, it seems, to distinguish between whether the attack is random or not. But if the graph is not random and has been created or its structure is the result of a particular design, then it matters what the nature of the attack. So for example, if you have a computer network, you would always assume that the attack is intentional. Now, if we go back to the star graph, we could change it somewhat. We could replace its central vertex with a path. In one sense, this is still vulnerable because the removal of a single vertex will disconnect the graph, but it will only disconnect it into two disjoint graphs rather than a collection of isolated vertices like we had with the star. So there's somewhat of an improvement. However, by improving it in terms of an intentional attack, we've made it worse in terms of a vulnerable attack, because now half of the vertices are vulnerable, where before only one was. It's very different how we address robustness and attack tolerance, whether we assume the attack is intentional or random. Now the star graph, let's talk a little bit about optimality. The star graph can be considered optimal in one sense, because suppose that it represents a computer network, and suppose that we want to designate some of the computers as servers, and the remaining computers are hooked to the server. But suppose that the servers are expensive. We would rather have people using the server and not providing the server. Well, if we only need one server, that is, everybody's joined to that one, then that is optimal in the sense of the cost. So oftentimes in optimality, you have conflicting constraints. When one goes up, the other comes down, and you want to find the optimum for both. So why don't we have just one server? Notice that we talked about the vertex being vulnerable, so even that would be the other constraint we would need. As you know from working with computers, we would need a backup. So this idea of needing a backup is highly connected with robustness. Biological networks are often very, very robust. And what makes them robust frequently is that there are backup systems. So since it seems that biological networks employ this idea of backup systems, and since when we design computer networks, also employ the idea of a backup system, could some concepts from graph theory be applicable to network science when the networks are biological networks? So we thought they might. So we're going to look at some graph theoretic measures and then apply that to a biological setting. Our first combinatorial measure is the domination number. So first we define a dominating set. A dominating set of vertices is a collection of vertices in the graph with the property that all of the other vertices have at least one adjacency in the set. So we have an example of a graph where we have 3 vertices that are slightly larger, and I claim that that is a dominating set. Each of the irregular vertices that stayed black have at least one adjacency in the dominating set. So you can think of it as the dominating set covers all of the other vertices with adjacency. Now, the dominating set of a graph is certainly not unique. You can choose a large number and easily dominate all the others. So it becomes interesting when you say, what are the fewest number of vertices that I can find that dominate the graph? So in this one, the fewest number that you can find is 3, the 3 that are selected. We can see it's a dominating set. We can also easily argue that you cannot use fewer than 3 because of the graphs, the vertices here on the periphery. They each have to be dominated, so they're either in the dominating set or they're being adjacent to one in the dominating set. So we have to have those 3. And then it's easy to see that those 3 are sufficient, so the best that we can do is 3, and therefore the domination number is 3. Now this is a variation on the domination number. It's called the locating-domination number. So we're going to use Peterson's graph to illustrate the locating-domination number. Now the red vertices here are a dominating set. You can check because all of the vertices that are not red are adjacent to at least one red vertex. So it is a dominating set. But we want it to have an additional property. The locating means we want to be able to say, given any vertex, what it's adjacent to in the dominating set, and we want that to be unique. Let me elaborate on the motivation for this. Suppose that we have a museum, and we want to set alarms in rooms of the museum that'll go off there if anybody enters the room. These alarms are very expensive, so we want to use the fewest number of alarms as possible. But we want to have enough alarms so that if someone enters a room, we not only know that someone has entered the museum, we know what room they are in. We will assume there's a different pattern for if someone enters a room where the alarm is, or if someone enters a room that's next to but shares a wall with the room. So what we have done is said every vertex represents a room, and two vertices are adjacent if they share a wall. Therefore, the dominating set will provide us a number for the sufficient number of alarms, because if we place the dominating set here, then every room is covered. Every room either has an alarm or it's adjacent to a room that has an alarm. And since this is a dominating set, we know that property holds. However, suppose that someone enters room 7. That will set off the alarm 6. But if someone enters room 10, that also sets off alarm 6. So we don't know where the burglar is. Is the burglar in room 7? Or is the burglar in room 10? We cannot locate the burglar. But with one additional alarm and a rearrangement, we can now not only cover all of the vertices, that is, cover all of the rooms with alarms, we can locate where the entry point is, because each adjoining room has a unique alarm pattern, as we can see in this table on the right. So now, if, for example, someone comes in room 6, then alarm 7 and 10 go off, as we've indicated here, and that is a unique pattern. So this is our locating domination number. It did cost us one additional alarm, but we did not have to put an alarm in every single room. So this is back to the combinatorial optimization again. We have conflicting constraints. In this case, we wanted the minimum number of alarms, but we wanted the maximum amount of coverage. So now we're going to apply this to a biological setting. First, we need to talk about the secondary RNA structure. So RNA sequence can be represented as a sequence from an alphabet of size 4, where the members of the alphabet are G, A, C, and U. So in this illustration, our sequence has 120 ribonucleic acids. And that's what these letters represent, the 4 nucleic acids. So if we start here, the beginning of our sequence goes G, U, 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 C, G, G, and so forth. It goes up and around and back and around, and then comes up and ends about where it started, with U being the last one. Now notice that we have areas that are open, and so those nucleic acids are not bound to another one. However, the dot indicates a molecular bond. So you can think of this in some sense as you have a string, but the string is sticky, and so in some places it's stuck to itself, and in some places it's not. The string is called the primary structure. Then when the string creates these molecular bonds, this is called the secondary structure. When these secondary structures bond together to form a three-dimensional structure, then we have a tertiary structure. So this is the secondary structure, or a schematic representation of the secondary structure of an RNA molecule. Now, the group at the Biomath Lab at New York University has a website where they have cataloged all secondary RNA structures as graphs. Some of the eRNA structures cannot be represented as a two-dimensional simple graph, such as this one. In that case, they use a graph with loops and multiple edges. But some of them can be classified as simple graphs. So they're in two different data sets. It's easy to see the modeling method. Each of the open regions are represented by vertices, and in the strands where you have the bonds, these are called stems, are edges in the graph. So now we want to employ our domination our locating domination and other domination parameters to see if they are indicative if we identify a tree, which is what this is, a graph, if we can identify whether or not it represents a secondary RNA structure by its domination number. So we looked and noticed that for the tree structures or the graph structures where they are known to represent a secondary RNA structure, the domination number tended to be higher. So this red graph represents a known secondary RNA structure, whereas the graphs that have not been verified to represent a secondary RNA structure have a lower domination number. And this makes sense because if you look, as the domination number goes down, we get back to this idea of vulnerability or robustness. If you have a star-like section here, if you were to remove this vertex, you would disconnect the graph. Now, for the locating domination number, the opposite seemed to hold, and that is that the locating domination number appeared in general to be lower for those graphs that represent a secondary RNA structure, as opposed to those that don't. Down here where we have the star-like structure again in a graph that does not represent an RNA structure, then we cannot select the central vertex for our dominating set and let that be the only one because of the idea that we do not know if attacked or if there's another molecule perhaps trying to bind to this one, whether that binding is happening here or here or here or here. So if we want that information to be conveyed, we would have to somehow signal each of these as a different location. That increases the locating domination number, whereas up here, the location dominating number is less. So it does seem as though that these properties of the domination number and the locating domination number are reflected in the secondary RNA structure. So we considered two parameters. Parameter 1 were the domination parameters that increased if the graph represented an RNA structure, and the second parameter, we used the domination numbers that tended to decrease if the structure was an RNA structure. So using an artificial neural network classifier, we can see that the red dots represent those that are known RNA structures, and the black represent those that are not known and considered not likely to be found in nature. And there's a clear-cut difference here. There's very little mixture. In fact, there's evenly divided as between those that are secondary RNA structures and those that are not. Now, if we use P2, that included the locating domination number. We do have a couple that are black here that are also mixed in with those that are red. Black are the ones that are not RNA-like, and red are those that are known RNA. The blues are to be determined. But still, we get a very nice separation of the graphs based on these domination parameters, where these graphs are being used to represent secondary RNA structure. So structural robustness and attack tolerance is a topic that is studied in theoretical computer science, and it also has, as we're finding out, applications in biological networks. There are a lot of interesting applications of graph theory in the study of biological networks, as we're finding out, and a mixture of both graph theory and network science are most helpful in finding out properties of these biological networks.